Welcome back and welcome to the wonderful world of fluid mechanics. Woohoo! Yay! So let's get started on our very first video. Starting with the importance of fluid mechanics. Lots and lots of applications, and I'll let you just read through these. I'm sure you can also come up with a whole lot more applications where fluid mechanics is important, because it is very, very important. Alright, so in fluid mechanics, what exactly do we care about? Well, surprisingly, it's not usually what's going on in the fluid itself, although that can be important to figure out what's going on, but it's more how the fluid's interacting with other objects. So typically a fluid mechanics problem is just the start of your problem. So what you do is figure out what the fluid is doing to some object, and then after that you do some kind of mechanics problem. So you're still going to have to remember that, for instance, the sum of the forces equals mass times acceleration, and if it's not accelerating, the sum of the forces equals 0, or a lot of times if it's rotating, don't forget sum of the moments are going to be equal to 0 also, as long as it's not accelerating. So Newton's second law, like I just wrote, still applies to fluid mechanics. So it is conservation of energy, conservation of mass, all of your typical laws that you use in physics. But why then do we need to have another class specifically for fluid mechanics? Well, fluids are more complicated normally. Okay, we're also a lot of times going to use control volumes, and you take those same laws, F equals ma for instance, and put it in a control volume. Now you need to reconfigure your equations a lot, because what is acceleration? You're not just following baseball going through the air, right? Another thing that makes it a little more complicated is usually you can't see what's going on in a fluid. You can see a baseball flying through the air, but you can't really see the different velocities inside of a fluid, for instance. And also a lot of times what you're going to find is fluids don't behave the way you might think they will. Solids can be a lot more intuitive than fluids. Okay, so just like every other class, we've got to start with a few definitions, a little bit of introductory material, not nearly as much as we did in thermo, but we still have to do a little bit of this. So first of all, definition of fluid mechanics. Okay, so like we said before, it's not only the study of fluids in motion or at rest, but also the effects that those fluids have on other objects. So the effects the fluids have on other objects. Okay, and a fluid itself, you all know what a fluid is, but let's get a little bit technical with it. A fluid is a substance with no preferred shape, and the other thing that tells us it's a fluid is it will just deform continuously if a shear stress or a shear force is applied to it, and it won't stop. And it doesn't matter how big that shear stress is, it's going to deform. Okay, so substance with no preferred shape and deforms continuously under applied shear force, no matter how small. And let's illustrate this by comparing a solid to a fluid. So first of all, if you have, say, this cantilever beam and you apply a force, P is a force, it's going to bend a little bit, right? But after it bends a little bit, it's going to be able to resist the force and it's going to stop moving. Instead, let's take a fluid, say this cup of coffee, remove the cup. The cup was holding it in place, keeping it from being under shear stress, and now gravity is going to apply a shear force. And the fluid is just going to start spreading out. And as long as there's still that force due to gravity applied to it, applying a shear force to it, it's going to keep spreading out until something resists it. It runs into a wall, or possibly surface tension could also stop it. So a solid, again, deforms until the applied load can be resisted. Okay, but now let's take off that load. What's going to happen? Well, it's going to return to its original shape. If we took the force of gravity off of that coffee, do you think it would return to its shape? No, it wouldn't turn into that coffee cup. It'd be just some kind of blob. So as long as the shear load is applied, it's going to keep deforming. As soon as you remove that load, well, it's not going to return to any particular shape. Doesn't return to original shape. And you can say it the opposite way too. So what we were just saying is apply a shear force and the fluid is going to deform. Well, the opposite is if you see that a fluid is not deforming, that means there must be zero shear stress. Okay, and that's a hydrostatic condition, which we'll talk about a lot in chapter 2. Okay, next, speaking about how complicated fluids are. For example, here this is smoke over for flow over a cylinder in a wind tunnel. All right, so very simple flow, right? Just flow going over a cylinder, no big deal. But look at what's going on. You got nice smooth lines here indicating laminar flow, it's called. Back here, though, it gets all chaotic. And that chaotic flow, that's called turbulent flow. Here, what you got going on is a wake, okay? Also called separation. We're going to see a lot of this stuff in the lab. All right, but just from this very simple flow, you can see how much more complicated fluids are than solids. Okay, and that's why it's a junior level class and not a freshman level class. A couple more definitions. A liquid, okay, it's a substance that retains its volume. So volume isn't going to change normally in a liquid unless under extreme circumstances. Do you remember what that's called? You should remember from thermodynamics. Well, I'll tell you what it's called. It's called incompressible. Okay. And the other thing about a liquid is it will form what's called a free surface under the action of gravity. So if you have a cup of water, the free surface is just where the water meets the air. Okay, that's the end of the water. And it's going to do this because the molecules have a lot of forces. They even though they will move relative to each other, unlike a solid, they have a lot more forces. They're a lot closer to a solid than a gas is. And so a gas is a little bit different. It has no definite volume, and it will fill a container, right? It will expand to fill its container. It can expand to fill its container. So you're not going to get a half full glass of air. Okay, and the molecules are spread apart a lot wider. Well, it's more separate than they are in liquids, and in fact, there are a lot lower intermolecular forces, and if we assume an ideal gas, that means that we're assuming there are no forces between the molecules in the gas. Okay, so we've kind of defined liquid and gas, talked about the differences a little bit. There are some fluids that are a little weird, and usually they're harder to categorize, and usually it's between a liquid and a solid. Okay, so for instance, toothpaste kind of acts like a solid, but let it sit there under the action of gravity for a little while, it'll start to deform like a fluid. Ketchup doesn't want to deform for a little while. Apply enough shear stress and then it really starts to deform. Sand is definitely a solid, but you can pour it like a liquid. And there's some other ones as well. Blood, cornstarch and water, we'll see some other ones. Okay, finally, for this rest of this little video, the continuum assumption. We've had this in thermodynamics, and what it really means is when we have, say, our control volume, and we're somewhere here on Earth, say, we can just define, temperature, pressure here, we got a velocity here maybe, and a different temperature, pressure, velocity maybe over here. We don't have to worry about, is there a molecule at that point or not? Because the molecules are so close together that we just don't have to worry about, is that point in between molecules or not. It's just kind of a continuous substance, thus the continuum assumption. If we were close to outer space, there'd be a molecule 1 and another molecule here, and the space between them might be a foot. That's the mean free path between the molecules. If you got a foot of empty space between molecules, well, things are going to be a little bit different, and this would be not a continuum. But that's like near outer space type of stuff. So for normal problems, we can consider that we have a continuum, and that just means we can define properties at a point. Okay, so stop here and go ahead and take quiz questions 1 through 3.